Hello student, I am Dr.A.K. Now I am going to discuss liquefaction of gases. It is very important. Liquefaction of gases. Last class I have discussed compressibility factor. Now I am going to discuss liquefaction of gases. Actually this is very conceptual. Gas, I told that there are three states of matter: solid, liquid and gas. Then all three are convertible. Gases, if you will, gases, you know that they are making far distance from each other and attractive forces will be less. That's why they will be far. Molecular distance will be more. Distance between the molecules will be more. But if you will try to bring them close, then how will you bring them close? Then two tools are there to bring them, two techniques are there, two methods are there to bring them close to each other. Then what are that two things? First, high pressure. If you will apply the high pressure, then molecules will come closer to each other. Okay. And second things, because always gas will be in movement, then now we have to slow down their movement. Then how it is possible? Then by decreasing the temperature. If you decrease the temperature, then kinetic energy will be less. When kinetic energy will be less, then movement will be less. Then there will be contraction, means they will come closer to each other. Molecules will come closer to each other. Then by these two methods, high pressure and low temperature, you can control the, control means here, you can now by applying high pressure and low temperature, you can bring molecules closer to each other. Then when they will come closer to each other, then their phase will change. They were in the gaseous phase in the beginning when pressure was low and temperature was high, reverse of this. And that time it was gaseous phase. Now you have reversed the case by applying the pressure and making the temperature low. Then gaseous molecules will come closer to each other. And then there is a limitation, range. Then they will come to that range, I mean molecules will come closer to each other. Then they will make a change in their phase. They will convert to liquid phase. Similarly, again if you will do further, means again further you will apply more pressure and low temperature, then again they will come further close to each other. But that will require very high pressure and very low temperature. Then again further they will come very close and they will come under the range of solid. Then see how gases are converting into liquid into solid. Correct? Then this are studied separately. This conversion of, that is called solidification. When from the liquid it is converted to solid, then it is called solidification. But when gases converts to liquid, it is called liquefaction. Then now liquefaction, we are studying here liquefaction. Then here little things, main things I told you, but now actually what happens, Thomas Andrew, one scientist was there, chemist, he has done this experiment. Okay. Then here just what he did, I will tell you, okay, because you are studying liquefaction of gases. First, complete data on pressure, volume, temperature relation of a substances in both gaseous and liquid state was obtained by Thomas Andrew on carbon dioxide. He did experiment with carbon dioxide. He has collected data, experimental data. After that, he plotted isotherms. Isotherm means temperature was constant, and he plotted a graph, pressure versus volume. Pressure versus volume. He has drawn the graph. Okay. He plotted isotherms of carbon dioxide at various temperature. That is called isotherms. Later on, it was found that real gases behave in the same manner as carbon dioxide. Okay. What carbon dioxides are behaving same way other gases, many gases, means real gases behave in the same manner as carbon dioxide. Andrew noticed that at high temperature, isotherms looks like that of an ideal gas. Andrews and noticed that at high temperature isotherm looks like that of an ideal gas. Means real gas is behaving like ideal gas, and the gas cannot be liquefied even at very high pressure. This he observed. Andrew noticed that at high temperature is very high. At high temperature, you know that gas will expand, volume will be more. Okay, this you keep in mind and think in mind also. And you notice that at high temperature isotherms looks like that of an ideal gas. At high temperature, obviously, because temperature is high, then molecules will be free to move at high temperature. Hence, looks that of an ideal gas. And the gas cannot be liquefied even at very high pressure. That time, when temperature is high, that time if you apply high pressure, then gas will not liquefy. This is important things. When temperature is high and pressure you are applying high pressure, then only by applying high pressure, gas will not convert to liquid. This you keep in mind. Then how they will liquefy? Then if pressure is high and temperature is also high, both are high, then it will not liquefy. Then what you have to do? You have to slow down their speed, molecules speed. Then how you will do? Then by reducing the temperature should be less. Then only their movement will be slow, and then if you will apply the high pressure, this is a condition. Temperature should be low, very low. And then you have to apply the pressure, high pressure. Then gas will convert into liquid. Then what should be the temperature? One temperature is fixed. He observed that temperature is 30.98 degrees centigrade. In the beginning, temperature was high and pressure was also high. Okay, pressure leave it high. But after that, when he began to decrease the temperature from high to low, slowly, then a temperature has reached. Then a temperature, after reaching at a certain temperature, decreasing temperature, it reached a temperature of 30.98 degrees centigrade. That time pressure was 76 bar. 76 bar. Pressure was high, means 76 bar, and temperature slowly decreasing when it reached to 30.98 degrees Celsius centigrade. Then that time, first time it was observed that now gas is converting into liquid. Then that temperature is called critical temperature. Critical temperature. And at that temperature, if we will apply pressure, high pressure, as for example 76, in case of carbon dioxide 76 bar, only then it will start converting to liquid. And then that pressure, at the critical temperature, what pressure is required to convert the gas into liquid? Gas into liquid. That pressure is called critical pressure. And at that critical pressure and critical temperature, what is the volume of 1 mole of gas? Volume of 1 mole of gas, that is called critical volume. And these three are called critical temperature, critical pressure, critical volume, that is called critical constant. Okay. Then here Andrew has done experiment and he has plotted pressure versus volume graph. Then because he did experiment at different temperature, then at a different temperature and at different pressure he did, then graph looks like complicated, but it is not complicated because he has done experiment at different pressure and temperature. Then here important point is that temperature, and at that temperature means 30.98, means roughly you can tell 31 degree, 31.1, but exact is 30.98. Then that temperature and 76 bar pressure and volume at these two temperature, what was the volume of 1 mole of gas? 1 mole of gas, 1 mole of carbon dioxide gas. Then these three things only has importance. In graph it is showing so many lines, so many curve. Then they are showing at different temperature and different pressure curve. That is not very important. It is just for comparative point of view. But main thing is that graph, nature of graph, curve, what he got at that particular temperature 30.98 and pressure 76 bar and volume, what was the volume? Then these three things, that is important. Then that three value I told you, three things is important, and you will find in the graph I will send you, you will find a graph just like a dome, D-O-M-E, dome. Okay. Then within the dome, D-O-M-E, means down volume will be more, and because volume you have to decrease, volume will decrease. Then how will you decrease? Then by decreasing the temperature and increasing the high pressure. If you will start experiment from the low temperature and low pressure, then slowly means not a high volume you have started experiment, high volume, then volume slowly you will decrease, then down will be more volume, and slowly you are decreasing the volume by applying the pressure, or increasing the pressure. then a pressure will come. That time you will feel that volume is decreasing. Volume is decreasing after increasing the pressure. And that time when pressure will increase at 76 bar, then that time volume will be very less, but gas will not liquefy. And when you will further, when you will decrease the temperature, then this volume will decrease fast, and at 30.98 degree, now volume will be very less, very less, and that time gas will begin to liquefy. Okay, then one point, just like a point you will find, then if you will make all this point you will add from the when volume was more, and how it was decreasing, then up to reaching the point it will give a shape of, it will take a shape of dome, D-O-M-E, dome. Then here you will find in this dome gaseous molecules, whatever where gaseous molecule was present in this dome, in this volume was decreasing from high to low, then it took a shape of dome. Then in this volume, what was the condition of molecules? That is important. Then here what was happening, that gaseous molecules, they were coming close to each other, and when after that when they are coming to close to each other, and temperature also you were decreasing, then a situation came, then gas and liquid, from the gas liquid was converting, and again liquid was converting to gas, means equilibrium developed, equilibrium developed. Okay, and this, due to this equilibrium, this gas was converting into liquid, and quickly it was converting into gas. Both were there, conversion of liquid, gas to liquid, liquid to gas. This was happening in this dome phase, in this situation, inside the dome volume. Gaseous molecules were in this situation, in equilibrium. Gas was converting to liquid, liquid was converting to gas. Then here one term came, vapor. Vapor term, you know that is the difference between the vapor and gas. Below the critical temperature, means 30.98, below that only gas will liquefy. Above that means 32, 33, 35, it will not liquefy. Only at that temperature, and below that only gas will liquefy. Then when this suitable pressure, in case of CO2 I told 76 bar pressure and temperature 30.9. Then here in this molecules, in this dome structure, they were in the vapor form. That gas is now called vapor, because that gas was below the critical temperature. Now gas will convert to liquid. That time gas is called vapor, because quickly it is converting to liquid, and again liquid is converting into vapor, because both can be done very easily. And that time gas is called vapor. This is important things. Difference between gas and vapor I told you. Vapor term you can use only when temperature is very low, means below the critical temperature. You have seen in water also, ice is converting into liquid, liquid is converting into ice. Okay, that time also equilibrium is there. Solid, ice is solid, then solid, liquid, liquid, solid. Then like that way there, when it is converting, vapor is converting into liquid in ice also, gas you can't tell, vapor. Because vapor, quickly it will convert to liquid, liquid it will convert to vapor, vapor, liquid, liquid, vapor. Equilibrium will be there. Then that is a low temperature. That time it will be below critical temperature. Then question of vapor arises when temperature is below critical. Then I have told you about the Andrews experiment. They have shown so many curve there, but you should not be afraid by seeing the different type of curve. Okay, now I am going ahead. All the gases, one more thing before going ahead, one more time I want to tell you that the temperature 30.98 degrees centigrade is called critical temperature. It is called TC, capital T, a small c. C means critical. Then 30.98 degrees centigrade is called critical temperature, TC, of carbon dioxide. This is only for carbon dioxide. Different gases have different critical temperature. Okay. This is the highest temperature. If you go from the downside, slowly and slowly temperature is increasing, then in that sense it is the highest temperature. Okay. This is the highest temperature at which liquid carbon dioxide is observed. Only at this temperature for the conversion to liquid. In that sense it is the highest and below that it will be liquid, but if you will go higher than this, means 35, 36, 50, then it is not possible. Then 30.98 degrees centigrade is called critical temperature of carbon dioxide. This is the highest temperature at which liquid carbon dioxide is obtained. Above this temperature, it is a gas. Vapor of volume of 1 mole of the gas at critical temperature is called critical volume, means VC, capital B, small c. Critical volume, and pressure at this temperature is called critical pressure, PC. TC, PC, VC. This is called critical constant. The critical temperature, pressure and volume are called critical constant. And again here you can understand, further increase in pressure simply compresses the liquid. Nothing will happen, only liquid will be compressed. Liquid carbon dioxide, it just simply it will compress the liquid carbon dioxide, and the curve represent the compressibility of liquid. That's enough. Now again further you just understand, all the gases upon compression at constant temperature, that is also called isothermal compression, show the same behavior as shown by carbon dioxide. Also by this discussion shows that gases should be cooled below their critical temperature for liquefaction. Critical temperature of a gas is a highest temperature at which liquefaction of the gas first occur. Liquefaction of so-called permanent gases. Permanent gases, I told you, oxygen, hydrogen, nitrogen, and helium, all are called permanent gases. Liquefaction of so-called permanent gases, that is, gases which show continuous positive deviation in Z value. Already I discussed, Z is greater than 1. Gases, permanent gas always will show positive deviation, means PV versus P graph. In that positive deviation above ideal line it will show. Okay, that is a characteristic of permanent gases. Then liquefaction of so-called means permanent gases, that is the gases which show continuous positive deviation in Z value, requires cooling as well as considerable compression. Compression brings the molecules in close vicinity, and cooling slow down the movement of molecules. Therefore, intermolecular interaction may hold the closely and slowly moving molecules together, and the gas liquefies. Already I have discussed. And here one thing again, new things, that the term continuity, what is the continuity, that sometimes question is asked. Many questions are asked. I am not telling arising questions because I am discussing in details. Then here continuity, what is important? Then here what is happened, that at 30.98 degrees centigrade and pressure I told you 76 bar for carbon dioxide. There what will happen, it is very difficult to tell that whether it is a liquid or gas. Liquid or gas, it is very difficult to tell because there only change is going on. You can't tell whether it is a liquid or a gas. It is a continuous process, equilibrium, continuous process. That's why it is called continuity. Continuity means continuously it is changing. Gases are continuously changing in liquid, and sometimes if minor change also, any minor change of, or you can say if even not, then both will be liquid to vapor, vapor to liquid, liquid to vapor, vapor to liquid. Continuation will be there. Okay, and below critical temperature it will be converting into liquid. Then that stage, that is called continuity state. Continuity state I have discussed in advance. This is difficult to understand, but I told in the right place. This happens only at critical temperature. Gas will convert to liquid, and same times it can be converted into gas also, means vapor also. Vapor, after the vapor, gas. Okay. Now again you understand further, it is possible to change a gas into liquid or liquid into a gas by process in which always a single phase is present. This is again important point. It is possible to change a gas into liquid or a liquid into gas by a process in which always a single phase is present. For example, what I have told in the case of carbon dioxide, we can see that these things at a particular temperature, that is a 30.9 at simple, 31 also you can tell, 31.1 exactly is 30.98. But for this continuity I am talking about, that means one phase. This change, for this change, means conversion liquid to gas, gas to liquid, that happens at 31.1 degree centigrade. Only at this temperature only one phase will be there. Only one phase will be there. Okay, that at the constant temperature along the, you can say, isotherm, okay, means 31.1 degree centigrade, the pressure will increase. 31.1 degree centigrade, okay, that the pressure will increase. Now we can move, you can say, simply you can tell in the graph it is telling so many things, but I am telling you that at this temperature, At this temperature, like 30.98 or 31 degree, you can tell that at that temperature only one phase will be there. Only one phase will be there, and only that time phase will change. That time, only that temperature, this will be there, liquid to gas, gas to liquid. Only one phase is required. And above this temperature, gas will be there. And below that temperature, liquid will be there. Okay, but at that particular temperature, continuity will be there. Means this equilibrium will be there. Okay. Now, again, I am telling you further. If a process is carried out at the critical temperature, substances always remains in one phase. This is important things. If a process is carried out at the critical temperature, substance always remains in one phase. This is important. Thus, there is a continuity between the gaseous and liquid state. The term liquid is fluid. One term is not liquid, fluid, F-L-U-I-D, fluid. The term fluid is used for either a liquid or a gas to recognize this continuity. The fluid term, fluid is used for both liquid and vapor. The term fluid is used for either liquid or a gas to recognize this continuity. Thus, a liquid can be viewed as a very dense gas. Very dense gas, in term of gas, you can tell very dense gas. Liquid and gas can be distinguished only when the liquid is below its critical temperature and its pressure. Below its critical temperature and its pressure. And volume lie under the dome structure, what I have told you. Because there in that dome structure, both will be in equilibrium. Since in that situation, liquid and gas are in equilibrium, and a surface separating the two phases is visible. That time you can see how both are changing. Both phase is visible in dome, in that area. In the absence of this surface, there is no, you can say, fundamental. Here, in the absence of this surface, there is no fundamental way of distinguishing between two states. You can't separate in the absence of this surface. Okay, you can see only liquid and solid phase in that dome structure also. In the absence of this surface, there is no fundamental way of distinguishing between the two states. At critical temperature, liquid phases. At critical temperature, liquid passes into gaseous state imperceptibly. Impercept is then from the word imperceptibly has come, and continuously. The surface separating two phases disappear. It will disappear. Okay, both will disappear. If this phase which we had one surface was there, and it was distinguishing both vapor and liquid. Okay, then the surface separating two phases disappears. Okay, as volume will decrease, means at that point. With that time only one phase will be there, that is the liquid. A gas below the critical temperature can be liquefied by applying pressure and is called vapor. Okay, a gas below the critical temperature can be liquefied by applying pressure and is called vapor of the substance. Vapor of the substance. Here you have to understand, a gas below the critical temperature can be liquefied by applying pressure and is called vapor, and that will be quickly converted into liquid and is called vapor of the substance. Carbon dioxide gas below its critical temperature is called carbon dioxide vapor. Critical temperature. Now I will tell some critical condition, critical constant value I will tell for some gases, because you should know, and sometimes in examination this value will help you. Then here critical temperature, critical pressure and critical volume I will tell for the some gases. As for example, first gas hydrogen, its critical temperature is 33.2 Kelvin. See, I am telling Kelvin. Then 273 plus T, correct? That is in Kelvin. Then 33 Kelvin means what? You have to, 33 Kelvin is there, then 33 includes, from 33 you minus 273, then you will get answer in degree centigrade. You will get in minus 33 plus 33 minus 273. Minus 273, you will get value in minus, and you will get value in minus. Then this is a very low temperature. Like that way for helium it is a 5.3, again very less. That's why these are called permanent gases. Critical temperature is very less. And pressure for hydrogen is 12.97, and volume is again further very less, 0.0650. And helium again temperature is 5.3 and volume is pressure is 2.29. and volume is again very less, 0.0577. Nitrogen 126 and temperature is 126 Kelvin, and this 33.9 pressure, that is in bar, and volume is again 0.0990. And oxygen Kelvin in Kelvin 154.3 and pressure is 50.4 and volume is 0.0744. Like that, carbon dioxide 304 Kelvin, pressure 73.9 and volume 0.0956. This I have told some critical constants value. Okay. Now I am stopping only here. Next class I will continue with other terms. Okay, thank you.